Okay, so thanks for inviting me. And I have to say this is, I have co-principal investigators on the project, Eike Mark Rinke and Alexander Woodke. I'm happy to present our work here today on what we think is a hidden universe of uncertainty in scientific research. And this research wouldn't be possible without our participant, co-author, collaborators. So big shout out to all of them. And we're really grateful that they all participated. And so the abstract we're going at here is this idea that science promises to basically investigate and report on uncertainty. And uncertainty, I'm sure as you all know, has many faces. So some interesting examples, maybe this opera group had claimed that they recorded neutrinos breaking the speed of light, but a second look at their data, in particular their instruments, suggested maybe that actually didn't happen. There's these ASH experiments, which are quite a long time ago now, but have been replicated over and over, where if you ask participants, not scientists, just sort of any participants to observe things, their observations will be shaped by the opinions of the others, what they think they're seeing at the same time, whether something moved or how big it is, et cetera. Something I've been working on, secondary observer effect, for lack of a better word, which is the same data isn't always the same data. I've worked with a lot of things like OECD data and indicators data, and they, up until maybe recently, didn't do like version controlling. So when I go to like try to replicate research, you know, my value for Australia in 1985 is different from yours because we downloaded the data at different times. It's really, you know, interesting thing that to come across at some point. But just to be clear, lack of uncertainty is rare. So consensus, or where something's like really clearly something, although it does exist. For example, here's the plot of carbon dioxide in the atmosphere over time, and sort of this very clear effect that humans are having on that value. Why is there uncertainty in science? I'm going to give a very broad category A, which is something like measurement error. It's a very technical feature of science itself. But as we know, and I think many of you are very aware, there's things we're becoming increasingly aware of today, such as, or what I would call systematically distorted research practices. Could be something like confirmation bias, where people sort of magically find what they expected to find in the first place, or competency biases, where people have different skills or experience or modes, things that shape the outcomes in some way. What I'm going to talk about today, or what I think our study gets at, is something we might call unsystematically distorted research practices. We don't have a best term for this, so maybe researcher variability is the one we're going with. And that is that the researchers themselves, just sort of their existence, produces some kind of variability. And thanks to Steve Velsko, if I said the last name right, for sending me a paper that calls this dark uncertainty, this sort of like dark matter. It's sort of, we know it's there, we know it affects outcomes, but it's really hard to observe. Could also just call it randomness. I mean, but randomness associated with the researchers, not with the data, just to be very clear. So our idea is that idiosyncratic researcher variability may generate more uncertainty in science than we are currently aware or had thought about. And to be clear, what we mean is really, this idiosyncratic variation is really at its core something that's almost undeliberate, where maybe I use Stata and someone else uses R, and someone else uses, I don't know, SPSS. And was that a choice? I'm not sure that was really a choice. We probably kind of just got brought into that through our training or our contacts, for example, and people who work at Stanford probably have access to almost anything, and our universities in Germany as well. But if you work in maybe a global South country, you don't have access to certain data variables or things which would then shape the results of the study, not because you chose that, but just because you happen to work there. So I just try to give some examples, or you might call it spooky variance, since we're kind of having this quantum physics theme in terminology. Just like, where does this come from? How could it be that the results are different? Strange. Sort of timely right now is this sort of pop science book that came out. You might call it that. I don't say that in like a disrespectful way, but it's intended for a broader audience. So, and the idea from Daniel Kahneman, who won a Nobel Prize, and some colleagues, is basically that there's noise in human judgment. So if you give humans the same information, they'll make different, very, very rational, but different calculations about how risky or what is the best plan of action and that kind of thing. So we're kind of making this analogous to how scientific research, noise in scientific research. Here's a good example. The question, does wealth lead to happiness, was asked of some participants, and they were shown this. And as far as I know, it was exactly this that they were shown. And they were said, okay, here's the data. Do you think that wealth leads to happiness? Not surprisingly, there were very different opinions in response. And, of course, this is a kind of classic, what you might call Simpson's paradox, where if you look at age groups, you see one thing. And, but yeah, so this is variability. We don't really know why they give different results. I mean, we can see that, yes, there's two ways of looking at this data. And this is a very simple example. There might be thousands of ways of looking at other data. Or there may be ways that I don't think about, that they're thinking about. And unless we sort of could tap into their brains or ask them, we wouldn't know. And again, thanks to Steve for sending me this paper. Something I know nothing about, but it sounds concerning, is lead in tuna. And this is a sort of meta-analysis, or it's just a meta picture of how much lead different labs have measured in tuna. And you can see the point estimates are quite different, but also the confidence intervals. And, when I look at this, other than being disturbed about, whether I'm eating tuna with lead in it, is how do we distinguish what is noise and what is like a distorted research practice? Maybe some are funded by the tuna, advocacy, so-and-so, and then others are funded by the anti-tuna. And then how do we distinguish what is really different instruments and different, calibrations and technical things like that? So the idea, the theory, let's call this a theory, is that if we could track all the steps in the research process, we could explain uncertainty. But this, like any social scientific effort that involves humans, means, we would need to know what's going on in every brain, at all times, and so much information that we don't actually have. But in theory, at least in theory, it should be possible to recover that. And so, since we also can't observe the same researcher in parallel universes doing the same research and possibly coming to different results, we have something which I think you're all familiar with, which is many analyst research, for lack of a better term. I tend toward crowdsourcing researchers, but many analysts seems to have stuck as a term. So you get many analysts, or basically scientists, and you give them the same hypothesis or hypotheses and the same starting data and say, okay, test it, to the best of your, test it independently, each one operating independently. But what's great about these, and some of these many analyst studies, this was not their goal, but you could remove systematically distorted incentives, so that's good, and could then potentially quantify noise by really observing the process, surveys, looking at their workflows, really trying to understand their ecological setting and they themselves, the researchers. And that was kind of what we were doing in our study. We started with about 100 teams. Some seemed to be sort of spam teams. And we had two big tasks. One was a direct replication of a study, just try to produce the same results, because, well, we had some other goals, but also many of these researchers, they had not seen this kind of survey data or even worked with this kind of survey data before. So we could also call it a warm-up. It turned out to be a lot of work. So we had about 85 teams complete the first replication part, and then 73 really stick it out till the end. and finish the part where we said, okay, you got a little taste for what it's like to work with survey data, and you've seen this hypothesis. Now you do your research. It's your turn. How would you design, the best possible test of this hypothesis? Of course, with the caveat, you have to use this data. You have to use these data and these particular outcome questions. That's the only way we can control it, and get. So we had 1 to 3 persons per team. We limited that by design, and the team submitted it. So immigration undermines support for social policy was the hypothesis. Immigration has like a negative effect on, if you like, and the team submitted 1,261 models in total. There was an average, a little over 12 models per team. I'll come to that in a moment. And we also asked them to draw subjective conclusions. Does your, do your findings support the hypothesis in your, professional opinion? Or if not, do they oppose it, which is kind of the, for our purposes, the natural opposite, or was it not testable given these data? And these are the questions, is about, from the International Social Survey Program, big cross-national survey, lots of cases, quite a lot of countries and many time points, but cross-sectional, not longitudinal, and questions about if the government should provide jobs or healthcare, old age care, unemployment, that kind of stuff. And kind of ideally 2 test variables, stock and flow of immigration, but because we wanted the researchers to be as much in their ecological, to have ecological validity, we got some other stuff. So it was a trade-off between how much we tried to impose and how much we could just let them be researchers. But mostly they used stock of immigration, the amount, and flow of immigration, how many are coming in and out, as the main variables. So that's how you end up with 12 models in the sort of ideal team. They have 6 dependent variables, these questions, and test each one for stock and for flow. But it ranged from like 1 to 100 models, the range, and some people made a scale and some people made multiple scales, and it was very interesting. We checked the results for replicability. That took forever. And if you're ever planning a study like this, maybe we should talk about it, because we were really understaffed and it was really challenging. There were like 5 software languages, and none of them could replicate, of course. So we had to go in constant contact with the authors and, oh, what is this? What is that? And
let's see, I think we lost.
I'm sorry, can you hear me?
Yes, I can hear you, and I can see people nodding.
I apologize about that. My headset just kicked the bucket. Anyways, let's just keep going. If you can hear me, okay.
Yes,
we had to
perfect.
We had to standardize the results. I can't possibly tell you everything we did in this short amount of time, so I'm trying to get the highlights here. Because we had the different distributions, people did a lot of subsetting. So they would, we are only going to study these countries or these time periods, or some people said it's only immigration flow that matters. We're going to focus on that. So we wanted to quantify how much uncertainty and why, pretty much. And so we had to qualitatively code in 5 coding languages their model specifications and try to come up with a scheme that represented their models. And we came up with 107 decisions, specifications, things that they did. And this also included their prior beliefs about the hypothesis and stuff like that, which software they're using. But kind of spoiler alert, in the dissimilarity matrix, every model was unique, at least on one feature, which is kind of the main finding. I'll get to that of this study. But here's how the results looked in terms of their point estimates. And these are just point estimates. There's no confidence interval there. They're color-coded in this traditional null hypothesis significance test manner, where the yellow ones are a negative effect, so immigration does ostensibly undermine support with the 95% confidence interval. Gray, not significantly different from 0. Bluish is positive. And then we have the weighted distribution of each finding across the models, because again, there were, different numbers of models per team. So that's the weighted distribution and results there. A slight majority with not statistically significant, different from 0. We have subjective conclusions. We have 88 subjective conclusions because some teams said stock of immigration and flow of immigration are actually independent tests of this hypothesis, or they're different tests. So they came to different conclusions for those, some of the teams. And so we have those conclusions above. This is also the specification curve style, and we have some of the variables below with a kind of heat map. I know your eyes will try to find the associations. Really, the only one is the percentage of positive test results that was in any given team would predict support of the hypothesis as their conclusion. The others, despite what it may look like, these are really not associations. And we can further kind of show that this way. Again, it's really hard to visualize all this data. But here on the left are the point estimates, the distribution of the point estimates, and on the right is the distribution of variance of point estimates within teams. Again, a potential outcome of interest. And there really isn't a raw association with these variables, nor is there much of a multivariate association with these variables: methodological expertise, topical expertise, attitudes, beliefs. And this is how we try to capture this, and probably, unfortunately, your little Zoom videos are covering the percentage unexplained variance. Maybe you can move that around to your liking. So then we use sort of typical multi-level models to try to explain within and between variance here showing you of the point estimates. And the yellow is unexplained variance. So we can't explain much. The top bar is total variance. The colors are assigned conditions, which we only had in the first study. We didn't think they would matter, but we thought it's important to just have them in there. They didn't matter. Research design matters a little bit, the green part. We can explain about 4% of the total variance with it. And the researcher characteristics, a tiny sliver. The between team variance, we could explain quite a bit more, 12% out of research design. But the within team variance, really little. And so you imagine the typical teams got their 6 dependent variables and identical models for each variable, each survey question. And there's like lots of variance. Okay, the natural conclusion is they're different tests, right? Healthcare, unemployment, these are kind of different policy domains. But because we didn't have a theoretical model, we're really just trying to explain variance. We use those as independent variables as well. Which dependent variable did they use? And still, this can't recover within team variance, meaning, yes, they may be different policy domains and lead to different whatever effects, but we couldn't explain them here using those domains. Finally, subjective conclusions, multinomial outcome, support, oppose, not testable. And now we have the adjusted deviance, because again, if you have 88 outcomes and throw in random variables, you're going to explain a lot of it eventually by throwing those in there. So it's adjusted deviance. How much can we explain of the adjusted deviance? And a bit more. Surprisingly, only 25% of it is from the percent positive test results, which I'll let you draw your own conclusions from that, but that should explain most of it, right? If we're sort of careful scientists, but there are a lot of ways to look at that. Okay, as skeptical meta-scientists, I'm sure you're thinking, oh, if I had that data, I would, they must have missed something. So we made an app that you can interact with and select which variables, you think might be this variable, that variable, and you can look at effects, p-values, and conclusions. Feel free to play around with it and let me know if you find something. But if you really, it's limited in its functionality. If you really want to test the variables, you would have to go to our GitHub repository. Although everything's there, reproducible, and you can, you're more than welcome. It's already there, publicly shared. We weren't sure if 4% was bad or good, so to speak, or was that a lot or a little, that we could explain 4% of the total variance. So to get a sense for that, we did a multiverse analysis of what seemed to be the most important variables, and then put them in all their different combinations so that we had like 5,000 models of these different combinations. And then we applied our predictive models to it. Again, this is in a single pipeline with a single software and a single research team running it. And we could explain 16% of the variance. So we thought this would then be a benchmark for which to evaluate it. And so we, of course, explained a lot less than that. And I think there's a lot of lessons in that, which I'll try to come to in the conclusion a little bit. We tried some other methods to do it, and you haven't seen it in this paper, but we've now started running some types of machine learning models based on our developing knowledge of these types of models to see if the machine can find something we couldn't. But basically, I think you can figure it out if you think about the degrees of freedom problem. We have 107 sort of specifications, so 107 variables to explain 1,261 outcomes. There's just a lot of empty cells. Each model is unique. That's the answer. Yes, we can explain all the variance if we just say each model is unique, and then we explained it. But what we were really surprised was that we can't explain much from certain specifications. I thought when we started this, the literature is really all over the place. It's a literature I'm familiar with. And I thought we're going to find some variables that are really key, the way that you do in a specification curve or a meta-analysis where you see like, okay, gross domestic product, if you include it, the results go this way, and if you don't include it, the results go that way. And I thought we were going to make some big steps forward in that regard. And I was, surprised that we couldn't, that we didn't. So if our results are at all representative of scientific research, and I'm not arguing they are, I mean, they certainly are in this area, and if there is an ecological validity, but if they are, there may be, we would say every step in the research process should be seen as non-trivial. And when I say step, I really mean like the hidden steps as well, right? We need to be aware that there are hidden steps. And some of them are crazy. I learned so many unusual things. For example, M+ version 8, which I have on my computer, and M+ version 7, which some teams had on their computer, with identical code produces different results because the default model parameter, some of the default model parameters were changed between those versions. And it took us a while to figure out what was going on there, that I couldn't reproduce their results. Right, so in conclusion, hidden universe of uncertainty or dark uncertainty. Different researchers performing seemingly identical tasks are prone to variability. We think, right? We don't have a smoking gun on that here because it's so broad, but this is what it hints at. And we think it's important to try to start communicating this type of uncertainty. We can't say much about the tested hypothesis other than we can't say much about it. So the results are very inconclusive in that regard. There's no consensus or anything like that. But given this hidden universe, we suggest something which a lot of you probably have worked on or are aware of, which is more epistemic humility. So not just because of publication bias, not just because of the threats of p-hacking, not just because of not enough replications, but also that there may be something else like researcher variability. But it's not all negative. I hope it may be a new opportunity for us to look at and explore uncertainty, which, as I understand, is what we do as scientists, and maybe embrace this. Again, thanks, Steve, for saying that dark uncertainty. And I'll end it with a quote, which is, I have to move my own thing to get it right. In formal logic, a contradiction is the signal of defeat. But in the evolution of real knowledge, it marks the first step in progress toward a victory. So thank you for your time, and I look forward to the discussion.